Well, good afternoon. I'm Wes Hines. I'm the Nuclear Engineering Department head here at the University of Tennessee. I'd like to welcome you to our Nuclear Engineering Colloquium program. Today's webinar is proudly co-sponsored by the Nuclear Science and Security Consortium. The NNSC is a multi-institutional initiative established by the National Nuclear Security Administration, NNSA, to train the next generation of nuclear security experts while engaging in development in the support of the nation's proliferation mission. The speaker today is Dr. Tomi Akindele. She's a former NNSC fellow and now a postdoctoral researcher at Lawrence Livermore National Laboratory. She received her PhD in nuclear engineering from the University of California, Berkeley in 2018, with her dissertation focusing on expanding the surrogate reaction to measure prompt fission neutron multiplicities from unstable actinides. She received her undergraduate degree from Texas A&M in nuclear engineering in 2013. Her current research focuses on applied antineutrino detection for monitoring nuclear reactors and the investigation of water-based liquid scintillator for next generation of kiloton-scale detectors. Welcome, Dr. Akindele.
Thank you, Dr. Hines, for that introduction. And so, like you said, my name is Tomi Akindele, and so the title of this talk is Applied Antineutrinos for Nonproliferation. So in the 1920s, when they first started doing measurements to try to understand the beta decay energy spectrum, they originally assumed that, similar to alpha decay, you would see a monoenergetic electron based off of the Q value of the reaction and then the mass of the individual components. However, when they did these measurements, instead what they saw was a continuous spectrum. And so the problem with this is if you have this continuous spectra that ends where you would expect this monoenergetic electron to be, it implies that there's missing energy. And so before they ruled that energy conservation was no longer occurring, they made assumptions saying that maybe the electron was scattering around in the cloud of the electron cloud of the daughter nucleus before it was emitted, and thus losing some energy. However, when they did a lot of calorimetry measurements, they noticed that there was no extra heat that was being produced. So there, in fact, was missing energy. And so this kind of brought up this anomaly that maybe energy isn't conserved. And so if we know anything about physical sciences, energy conservation is one of the most fundamental laws that we know of. And so 10 years later, Wolfgang Pauli, he mentions that I have done a terrible thing. I've postulated a particle that cannot be detected. And so he postulated that the reason why there was this missing energy was due to the fact that beta decay was a three-body problem. And so it's not just your daughter nucleus and the beta particle that's also emitted, but you also have an antineutrino that's emitted, or a neutrino, depending on if it's beta minus or beta plus decay. And so by carrying away momentum and energy, he's assuming that there's this ghostly particle with zero charge and little mass, which explains why you wouldn't see it in your detectors, that was causing this continuous shape. And so if you look at the energy, the play-on of energy between your beta particle and your neutrino energy, they tend to sum towards the Q value of the reaction. And so any energy that you don't have from the, in this case, this is a beta branch, which is why you have a neutrino branch. So any energy that you don't have within your beta branch effectively is carried away with your neutrino branch. And so when you look at an entire isotope that might be decaying to a more complex decay scheme, you would see that in the red here, for instance, you would see multiple contributions to a beta spectra. And similarly for an antineutrino spectra, because this decay corresponds to this decay scheme that we see for magnesium 56, you see multiple contributions of this continuum from the antineutrino spectra. And so that's from one decay, or this cumulative decay for multiple branches over time. And so now, if we focus on nuclear reactors, they're a copious source of antineutrinos. And so we know from nuclear engineering that if you have a neutron incident on some sort of fissile isotope, whether it be uranium-235, plutonium-239, et cetera, that you have a lot of fission. And so when you have fission, you have about 200 million electron volts that are emitted as long as neutrons. But something that we don't talk a lot about are these daughter nuclei. And these are extremely unstable isotopes. So we know that as you get higher up in proton number, you're going to have relatively more neutrons to combat Coulombic repulsion. However, when these isotopes break apart, and now they're a lot smaller in mass and have a smaller proton number, they don't necessarily need all of these neutrons. And so that's why they tend to rapidly beta decay. And something else we know about the beta decay of these fission fragments is based off of what actinide that you're specifically looking at, they're going to have variable fission fragment yields, as we see here on the left, right? So the distribution for uranium-235 is going to look very different than the distribution for plutonium-239 and other isotopes that would undergo fission. Another thing to remember is that for every fission, you have roughly 100 different isotopes with roughly 8,000 different beta branches that would decay. And so as we saw in the previous slides, that when you have one beta branch and then one antineutrino, you have the spectra. And if you had a more complex beta scheme, you would have multiple spectra that would sum to get a cumulative distribution. But then for uranium-235, plutonium-239, and the other two isotopes, or the other two major actinides, you see that the beta branches, or then the corresponding antineutrino branches, are really a sum of roughly 8,000 different branches. And so because they each have their own unique distribution for the fission fragments, each one of these different isotopes are going to have a very unique antineutrino emission based off of their decay. And so you see this for uranium-235, plutonium-239. And so when they're all plotted together, and so this is the antineutrino energy as a function of relative to the fission or the emitted fission, you'll see that they all have different shapes, right? So not only do they have different shapes, but they also have different amplitudes. And so depending on what is going on in your reactor, what is undergoing fission, the antineutrino emission is going to look very different. And so again, nuclear reactors, they produce a lot of energy. And so if you have roughly 6 antineutrinos that are released per fission, then you could expect about 10 to the 21st fissions per second from about a 3 gigawatt nuclear facility. And so in total, that's about 10 to the 22nd antineutrinos per second. And so that's a huge number of antineutrinos that are emitted just from a single nuclear reactor complex. And so why antineutrino monitoring is still difficult, or why antineutrino detection is still difficult, is because antineutrinos are extremely weakly interacting. And so in antineutrino detection, I'm only going to be focusing on inverse beta decay, which is the only one that's actually been demonstrated. There's 7, but that's only been shown in principle, never in front of a nuclear reactor. So for inverse beta decay, you have an antineutrino that's incident on some sort of proton in your media. So if you have scintillator, you're going to have a lot of quasi-free protons. If you have water, similar to that as well. And you get a positron-neutron pair. What's important to know is that because the positron is significantly lighter than the neutron, that's going to carry away most of your energy. So you'll know the energy, you can induce the energy of the antineutrino based off of the energy of the positron, minus 1.8 MeV, because that's the key value of the interaction. But then if we look at the cross-section for this interaction, we see that it's on order of 10 to the negative 42 centimeters squared, and it scales as a function of the energy of the antineutrino squared. And so when we think about typical nuclear reactions, right, a barn is roughly 10 to the negative 24. So this is significantly more, this has significantly smaller interaction probability than what you would tend to see from a typical nuclear interaction. And so the emitted spectrum from an antineutrino tends to fall down as a function of energy. And the cross-section, as I showed before, goes up as a function of the energy squared. And so a pretty typical shape that you would tend to see from an antineutrino detection is this hump-like shape, just due to the fact that your emitted spectrum decays as a function of energy and your cross-section increases significantly as a function of energy. And then when we look at this for all the different major actinides, as I mentioned before, right, each one of these has a different shape. So U-238 tends to give off more antineutrinos per fission and has a tends to give off more antineutrino emissions per fission relative to plutonium-241 and 235. And then 239 tends to give off a significantly lower amount. And so why this is interesting is you can actually induce some information about what's going on in a nuclear reactor, right? So for instance, if I look at this figure on the right, it shows the days into the cycle and the fission fragment, the fraction of total fissions for different isotopes. And so when you begin a nuclear reactor, most of your fissions tend to come from uranium-235. However, through neutron capture, you start to breed in plutonium-239. And so towards the end of the cycle, most of your fissions are coming from plutonium-239. So if we're looking at the shape in the center right here, and plutonium-239 gives off less antineutrino events relative to uranium-235 for fission, you can imagine that throughout the cycle, you're going to see a decrease in the amount of antineutrinos that are emitted. And this was something that was actually demonstrated in subsequent experiments, as I'm going to show in a few slides. And then one other thing that's important to understand about antineutrinos is that they oscillate. And so what I mean by antineutrinos oscillate, I mean that if you start off with an electron type antineutrino, over some distance, you won't have all of those electron types antineutrinos. They will turn into other flavors of antineutrinos that you can't necessarily see in your detector. So if you're detecting something, an antineutrino using inverse beta decay, you are only sensitive to electron type antineutrinos. And so if in this demonstration right here, you see that some antineutrinos, electron type antineutrinos, will oscillate to a muon type antineutrino or a tau type antineutrino. In some cases, they might actually oscillate back from an electron type antineutrino to a muon type antineutrino, and then back again to an electron type antineutrino. And so there's a series of matrices called the PNMS matrix that dictate how these oscillation parameters work. But if we write out the full formula, we see that there's a near field component and a far field component. So what I show in the center is antineutrinos, the survival probability of an antineutrino as a function of distance. And so if you look at this, this figure, you'll see these very fast wiggles, as well as these really long oscillating features. So the very fast wiggles are dictated by the near field oscillation parameters, which is the 3-2 values, so mostly delta m squared 3-2. And then when we look at the far field oscillations, and so these are what you see right here, these really long, this longer oscillation form, and that's dictated by your far field oscillation parameters, or the 2-1 values. And so in the context of far field reactor monitoring, the 2-1 is really interesting to us. We are likely insensitive to the 3-2. And so if we were to take a snapshot of this survival probability as a function of different standoff distances, what you'll notice is it's not just the total rate of antineutrinos that have oscillated, but it's also a distortion in the actual energy spectrum of these antineutrinos. So in purple, we see a spectra that would have been detected at a 5-kilometer standoff. In blue, we see a spectra that would have been at 26 kilometers. And then in black, we see at 60 kilometers. And so at about 5 kilometers, we see that there's not really a lot of distortions in the antineutrino spectra, just because you're not that far away. However, once we get to 26 kilometers, we see a lot of contributions from the 3-2 oscillation parameters, specifically these wiggles that we see here within this blue spectra. Whereas when you get a lot farther away, so roughly 60 kilometers away, as we're showing the black, you actually see the contributions from both the 3-2 and the 2-1 oscillation parameters, right? So you see the 3-2 from these really fast wiggles, and that's again your near field component. And the far field component shows up within these really slow oscillating features right here. So if you can kind of squint, you can see that there's this binodal hump in a way, and that's a indication of the far field oscillation parameter. Okay. And so antineutrino monitoring or antineutrino detection has kind of been around for a while, since the 40s, or the ability to detect antineutrinos. But it wasn't until recently, about 20 years ago, that antineutrinos were actually proposed to possibly help with monitoring nuclear reactors. And so again, in a nuclear reactor, we know that if you have a neutron incident on uranium-238, it'll turn to uranium-239, which will beta decay twice to plutonium-239. And as I showed before, there's information that you can understand about what's going on in the nuclear reactor based off of the fissile fraction or the fissile quantity, and what we then see in the antineutrino spectra. And so we propose, or others, and I have proposed antineutrino monitoring as a tool to help in the IAEA's missions or nuclear monitoring missions. And there's been some demonstrations of this technology in the past. And so the first one of which is called the SONGS detector. And so the SONGS detector was deployed at the San Onofre site in California. San Onofre is no longer a nuclear reactor there, and so that project ended because the nuclear reactor was shut down. And so this was located in the Tandem Gallery at a 25-meter standoff from a nuclear reactor. And so the actual detector is about like half a ton of gadolinium-doped scintillator. And so this was one of the first demonstrations that you can actually use antineutrino monitoring to verify the power of a nuclear reactor. And so on the right, I show their results. And so what they show is the reported power of the nuclear reactor. So this is before a shutdown, during a shutdown in the center right here, and then after shutdown. And what they show is that you could correlate the antineutrino emission to the actual power of the nuclear reactor. So when the nuclear reactor is on and fissioning isotopes, you saw antineutrinos. When it shut down, you still saw antineutrinos, but at a smaller concentration. And then when it came back on again, you again saw antineutrinos. So this is a pretty great demonstration of your ability to verify the power of a nuclear reactor. However, when they actually closed in on the antineutrino events, they show that towards the end of a reactor cycle, right, they have a lot less counts than at the beginning of a cycle. And that was one of the first demonstrations as well of the fact that you do have some information as to what's going on within the nuclear reactor of the fissile inventory just by looking at the antineutrino emission. And then something else I wanted to point out from this plot is I mentioned that in an antineutrino, when you look at antineutrinos from a nuclear reactor, you get about 10 to the 22nd antineutrinos that are emitted per second. But when we look at the actual count rate as a function of weeks, you see that they only get about like 400 counts per week, right? And so, 400 counts per day. And so you see that, because this is averaged over a week. And so you can see that despite the fact that you have a large signal, the interaction cross-section makes it such that you're not going to get a lot of counts, but again, still with like about 400 counts, it was sufficient to actually demonstrate verification of the reactor power and some information about the fissile inventory. And then Patrick Huber at Virginia Tech also demonstrated that you can use antineutrino monitoring to understand more information about the fissile inventory if you're looking at the energy emission, the energy profile of the antineutrino. And so he demonstrated through simulations that if you were to monitor the heavy water reactor in Iraq, Iran, that if you had a loss of continuity of knowledge and at the beginning of the shutdown or the beginning of the cycle, so 45 days within the cycle, you made a measurement of the antineutrino emission. And then about 400 days in the cycle, if there was some sort of loss of continuity in knowledge, you could just do a simple chi-square fit of the different cycles and see that you have a substantial difference. And so they see a chi-square of about 30. And so here they show the plutonium content that they were showing for 45 days. There's a loss of continuity in knowledge, and about 8 kilograms of plutonium is removed from the nuclear reactor, and they started back up again. And they're able to show that you can see within about like 5.6 sigma that there's a difference in the count rate that you would, or the energy spectrum that you're expected to see. And so this is a pretty good demonstration of how you can actually use antineutrino monitoring on something like a heavy water reactor to see if plutonium is in fact being diverted from the nuclear reactor. And then another case of antineutrino monitoring that was done at Livermore, as well as Georgia Tech, was to propose it for plutonium management and disposition. And so within the NPT, one of the clauses does state that nuclear weapon states need to actively be working towards disarmament. And one treaty between the US and Russia that, a former agreement that I guess was later disbanded was plutonium disposition. And so the idea was that you could take weapons grade plutonium, mix it with uranium to make some sort of mixed oxide, and then burn it in a nuclear reactor to make it unusable for nuclear weapons purposes. And so they demonstrated that you can use antineutrino monitoring to determine what the actual core makeup of the nuclear reactor is. And so, for instance, if you had a light water reactor or if you had LEU fuel, it's possible that in this sort of verification scenario, one party might try to spoof the other by, instead of burning MOX fuel, just burning lightly enriched uranium, or burning some sort of different concentration of the mixed oxide, or just using mixed oxide with reactor grade plutonium. And they demonstrated with that with antineutrino monitoring, you can actually determine what's going on in the nuclear reactor so that you understand if they're actually burning reactor grade, if they're actually burning weapons grade plutonium, or if the reactor core is being made of something else. And so that's just another example of how antineutrino monitoring has been proposed as something that could be useful for nuclear nonproliferation and nuclear safeguards. And then lastly, the last example I'll show is the use of antineutrino monitoring for advanced fuel types, specifically thorium fuels. And so with thorium reactors, they sometimes have been stated to be a lot less, that they're more proliferant resistant than your typical LEU reactors because they don't breed plutonium. However, with a thorium reactor, now you have a neutron on thorium-232, turns into thorium-233. And again, 2 beta decays away, and now in this case, you have uranium-233. So yes, it's not plutonium-239, but uranium-233 is still fissile and can actually still be used for nuclear, for a nuclear device. And so we demonstrated in a paper a few years ago that if you had a thorium reactor, you could use antineutrino monitoring to actually determine whether or not they are using the uranium-233 as subsequent fuel, or if they're removing uranium-233 and replacing it with LEU. And so we demonstrated that the antineutrino spectra for uranium-233 is significantly distinct from that of uranium-235, such that if you were to look at the count rate as a function of time, and then you had some sort of anomalous event and where like material is being removed during an online refueling cycle, that you would actually see a pretty significant distortion with the event count rate. So this is, again, a way that you can actually apply antineutrino monitoring for like the next generation of nuclear reactors. Okay, and so then everything I've shown you about reactor antineutrino monitoring with, or reactor monitoring with antineutrino has been done within the near field. So all these case studies, all of these demonstrations, they all occurred within a few meters of a nuclear reactor. And from these case studies and demonstrations, they were able to show that antineutrinos are weakly interacting. And so this is really great because you can't shield the signal. You couldn't put layers of lead in front of your detector. And so you can detect them at longer standoffs on the order of meters. The antineutrino emission is directly proportional to the reactor power. So this gives you some real-time monitoring of the reactor operational status, as well as the fact that antineutrino energy emissions is dictated by its parent isotopes. And so you have some information about the relative fuel burnup in the fissile inventory. And so we demonstrated in previous case studies why that could be interesting for nonproliferation. But one question that we now have is, well, we know antineutrinos are weakly interacting, and so we could possibly detect them on the order of kilometers, even further away from their location of interest. I mean, we have antineutrino detectors that literally can see antineutrinos from supernovas or neutrinos from the sun. So our question is, well, what can we do in the far field? Like, how far away can we be and still see antineutrinos, and how can that be useful for the safeguards purposes? And so that's why we have neutrino experiment 1, and so or antineutrino experiment 1, which is also referred to as NEO or NE1 sometimes. And so this is intended to be the first demonstration of reactor monitoring in the far field. And so one thing that we know is that because we're now in the far field, in this specific instance, 25 kilometers away, we're going to lose a lot of spectral capabilities and high statistics, right? So because we're further away, we still have 1/r² effects or solid angle effects. And then we also have oscillation effects that's going to lower our signal. And so we're going to have a higher degree of non-intrusiveness, but we're going to get a lot less information from our signal. And so the whole point of this exercise, or the whole point of this experiment, is to really understand what can we do now that we're actually in the far field. And so the collaboration that this is kind of under is also called the WATCHMAN collaboration. And so this refers to the water Cherenkov monitor of antineutrinos. There's a lot of name changing going around, but the collaboration itself is called the WATCHMAN collaboration, and I'll just later describe the name of the site and the name of the detector. And so this collaboration has about roughly 100 collaborators from 19 institutions between the United States and the United Kingdom. And so on the US side, our main funder is the NNSA for NE1. And then on the UK side, the main funder is the Ministry of Defense. So we have the Atomic Weapons Establishment, which is their nuclear lab in the UK, as well as a lot of different universities in both the US and the UK. And so the detector that I showed before is about where the gadolinium water concept for the detector is 20 meter high by 20 meter wide. So it's a 20 meter right cylinder. And it's going to have about 4,000 PMTs, photomultiplier tubes, some that face inwards to look for a signal, and some that face outwards to reject muogenic events, such as fast neutrons and muons that come through the detector. And so for this design, I'm describing a 1% gadolinium-doped water design. However, there are other fills that are under investigation, such as water-based liquid scintillator, and then also the possibility of using light enhancement tools. And so the deployment site for Neutrino Experiment 1, and so again, I say it's going to be 25 kilometers away from a nuclear reactor. So in the UK, on the eastern seaboard, there's the Hartlepool reactor complex, which has about 3 gigawatts of installed nuclear reactor power. And so 25 kilometers away, it's actually closer to 26, is where Neutrino Experiment 1 is supposed to be located. And so this is the gadolinium-doped detector that I spoke of. And this is going to be housed within the Boulby underground laboratory. And so there's already an existing laboratory within this potash polyhalite mine in the UK. So they used to do dark matter experiments there. And so we're putting in our detector, or hoping to put in our detector, to now do underground antineutrino measurements. And so this is about 1,000 meters underground. And again, this is a joint US-UK led effort. It's occurring in the United Kingdom for this specific experiment. Okay, and so again, I mentioned that we detect antineutrinos through inverse beta decay. And when we have a water detector, what happens is you have an antineutrino that's incident on a proton within your gadolinium-doped water media. And so when you have inverse beta decay, you have a positron-neutron pair that's produced. So as this positron is produced, it's going to carry most of the kinetic energy of the antineutrino, and it's going to give, if it goes above the threshold for Cherenkov light, it's going to give a Cherenkov cone. And the idea is that this Cherenkov cone is detected by our array of PMTs. The neutron, however, will scatter around on the protons within the water, and then capture on gadolinium. And so neutron capture on gadolinium releases this large gamma ray cascade of energy, about 8 MeV. And so when you have 8 MeV of gamma rays that are emitted in the water, you now have, it's not like a scintillator where you are likely to see all 8 MeV of those gamma rays that are emitted, because we're now looking at Cherenkov light, right? So anytime you have a gamma ray that's emitted from this 8 MeV cascade, it tends to be separated into different gamma rays. And so the only gamma rays that you're actually going to see are the gamma rays that have enough energy to Compton scatter an electron, and that electron then having enough energy to be above the Cherenkov, the Cherenkov threshold. And so instead of seeing the full 8 MeV energy deposition, we tend to see about 4 MeV based off of the fact that we're such a threshold experiment. But again, if we see the positron and then a delayed neutron based off of the light emission, then we can say that we've seen an antineutrino. And so we use a JANT4 based simulation package to understand our response. And then we reconstruct these events using a tool called Bonsai. which was originally developed for the Super Tomi Akindele experiment, but we're now using it for our detector. And so if we look at these particles, so the positron and delayed neutron, if they're separated by a time of 100 microseconds, so that's to give enough time for the neutron to thermalize, and 2 meters in voxel space, then we call that an inverse beta decay event. And we use 2 meters just based off of how well we can actually reconstruct these events. They're usually likely to capture within centimeters of each other. Okay, and then for the positron response, so instead of using energy, we use an analogy for energy, and so that's the amount of PMTs that actually fire within 9 nanoseconds. And so if we see this figure right here, when we have the PMT timing distribution, most of the events tend to be within 9 nanoseconds of the reconstructed location. And so most of the events, to rule out a lot of background, is what we see within the first 9 nanoseconds of an event. And the reason why we use PMT hit times is because we see about 9 photons or 9 photoelectrons per MeV. And so we don't really have a great handle on our energy resolution if we just use how much light we see, especially if you have like PMTs firing, dark noise, etc. So our most stable analogy for energy is actually our PMT hit time. And this is fine because if we look at the PMT hit time in the center as a function of the number of PMT hits that we see 9 nanoseconds or N9, we see that's pretty linearly above 1 MeV for the positron energy. It's pretty linear to the actual positron energy response. So it's a pretty good analogy. And again, I mentioned that we reconstruct, if we see 2 events, so the positron and delayed neutron within a 2 meter reconstruction location, that's how we determine an event. And that's mostly because if we look at the reconstruction as a function of positron energy in our detector, we can really only, again, above about 2 MeV, we can only reconstruct our positron location to about 2 meters within our detector. So it's not 2 meters because we expect them to happen within 2 meters of each other. It's really 2 meters just based off of how well we're able to actually reconstruct our events. Okay, and so some of the non-proliferation goals, or the 2 non-proliferation goals specifically that I've looked at for this detector or these detectors is, the first one is, well, how well can we exclude the presence of a nuclear reactor, right? So which we call our exclusion scenario. So there can be some non-proliferation cases in which you have an agreement with another country to say that within this specific region, you're not allowed to have a nuclear reactor. And so could you put an antineutrino detector in that location to verify that there are no nuclear reactors? Or how well could you actually see a nuclear reactor above background if you're trying to find a nuclear reactor? Additionally, our second non-proliferation goal is how well can the presence of a known nuclear reactor be confirmed? And so in the case that you know that there is a nuclear reactor on site, it's possible that maybe they have a smaller research reactor also close by that uses a lot of the same facilities and a lot of the same infrastructure for a nuclear reactor that's not declared. So if you had a if you had an antineutrino detector, how well on top of the expected signal that you're expected to see, can you see another nuclear reactor that hasn't been declared? In this case, we call it our verification scenario. And then also within our verification scenario, we also want to see, can we actually range the location of nuclear reactors? If we actually know, can we actually figure out where they're supposed to be based off of the fact that you have distortions in your antineutrino energy spectrum from oscillations? Okay, and so to do this, we first have to understand all of our signals and our backgrounds. And one problem that we have, because we're an antineutrino detector, is that we see antineutrino backgrounds. And this is actually going to be our single largest background within our detector. And so I mentioned that we're 25 kilometers away from the Hartlepool reactor. And so 82% of the antineutrinos that we see are going to come from the Hartlepool antineutrinos. However, there's also another nuclear reactor site that's about 150 kilometers away called the Haysham reactors. And those contribute to about 11 to 10% of our antineutrino emission. And so the rest of the United Kingdom reactors are going to contribute to about 3%. The French reactors, we see some of those, about 2%. And then the rest of the reactors from Belgium, Netherlands, and Germany contribute about the other 1.5% of the antineutrinos that we're going to see. And so we use this tool called geoneutrinos.org to understand our antineutrino backgrounds. And then in addition to antineutrinos from nuclear reactors, we're also going to see geoneutrinos from uranium and thorium in the soil. And so thorium, luckily, the antineutrino emission is about lower than 2.6 MeV, so we don't expect to see a lot of those antineutrinos within our detector. However, there are some contributions from the geoneutrinos from uranium that may leak in, and so that's a background that we quantify as well, along with the rest of the world reactor background. And so whenever we talk about this deployment in the UK, we tend to refer to it as a high antineutrino background location because of how many nuclear reactors there just are within the general region. If we were to reproduce this experiment in the Southern Hemisphere, we would expect that our backgrounds would actually be a lot lower. And so we know that nuclear reactors shut down in variable times, and so we know that our signal isn't going to be constant. So as a result, we associate about a 5% systematic uncertainty to the antineutrino background flux to accommodate the fact that the nuclear reactors will be turning on and off without our knowledge. Okay. And then we have other backgrounds aside from the backgrounds that are shockingly similar to the signal that we want to see. And the first of which we refer to as accidentals. And so accidentals are really just gamma rays and beta rays from just normal radiation decay or radiological decay within our structural components, right? So we know that there's going to be trace amounts of uranium and thorium in the water. We know that stainless steel has some amounts of like cobalt 60, cesium 137, potassium 40, et cetera, right? We know that these radiological decays exist in nature, and so they're going to exist within our detectors. And so if we were to see two gamma rays that occurred in close time and close space coincidence, it might look like an inverse beta decay. And so we have to understand that background to understand when we're actually going to see our signal. Additionally, we're going to have contributions from muogenically induced fast neutrons. And we call these correlated backgrounds in the sense that you would have a muon that will go through the rock that surrounds the cavern and the location in which your detector exists. And it's going to make really high energy neutrons. And so you might see those neutrons if they interact within your detector by, the neutron can interact with oxygen and knock off more neutrons. And if both of those neutrons are detected in close time coincidence, that might look like an event. Or you could have a high energy neutron that goes through your detector, knocks off a neutron, and then both of them get captured. That might look like an inverse beta decay event. And so we just have to classify and understand the fast neutron backgrounds as well. And then the last background, well, not the last background, but another background that's also pretty important to understand is our radionuclide decays that are also muon induced. So what happens is if a muon goes through your detector, it will make these very light nuclei that decay through beta delayed neutrons. And so they'll release a beta particle and then have a neutron that's also emitted. So these two events are going to look shockingly similar to your inverse beta decay event. And that's why it's also important that we like correlate them as a function of time within our detector. And so for the accidentals, within the full simulation framework in JNOT4, every single component within our detector is included, as well as the radiation within them. So we simulate the radiations from the PMT, the radiation in the water, the PMT holders, the cable, the tank, the concrete, the rock. All of those go into our simulation-based framework to understand how frequently we're going to see something that might mimic our signal of interest. And so if we look at the accidental distribution, we can see that in this case, we tend to make a cut on the distance from the PMTs. So we only include events that occur within a meter from our detector, just to remove a lot of the backgrounds from the concrete and the rock, and et cetera, as well as the PMTs. Additionally, if we actually look at the energy distribution of our accidentals, we'll see that like close to the very low PMT firing events, we see a really large signal in the background. So really the radiation from the rock and concrete gives us the most events within our detector. However, by employing a high energy cut, we can actually reduce most of these events. And so this is a cut that we usually use for our delayed events of roughly having more than 15 PMTs. And so as a result, we can actually remove a lot of our backgrounds from the concrete, the tank, the rock, etc. And so now our number one background from accidentals tends to come from the PMT, so the photomultiplier tubes that are actually detecting the signal. And that's just due to the fact that they are made of glass, and glass has a lot of potassium as well as uranium and thorium contributions. Okay. And then for our fast neutrons, to actually understand our fast neutron background, a few years ago, we had a gadolinium-doped water detector that was called the WATCHMAN detector that was deployed in the Kerf mine. And the idea was that we would use this smaller, about 2-ton gadolinium-doped water Cherenkov target to understand our simulations and to see if our simulations can reproduce this experiment. And so this was actually verified by a graduate student at University of Michigan. So this is Felicia Sutanto, who should be graduating soon. And so what she did is she investigated different simulation packages to see what could actually reproduce our experiment. And so for instance, our data that we had from WatchBoy is shown in this gray color. And then when we did the J-4 simulations, we saw that they overestimated our detected neutron multiplicity significantly. So if you see 2 neutrons, or 3 neutrons or 4 neutrons for your detected neutron multiplicity, we really care about the 2 neutron contribution because that's what's going to look like an inverse beta decay, because we veto excess multiplicity events. And so she showed that by using the Fluka simulation framework, and then for the neutron production, we were able to get better agreement with our actual data. And so that's what we now use within our simulation framework. So taking in the Fluka inputs into J-4, I was able to understand what the dineutron detection limit is by looking at the 2 neutron detection in the detector. And so in green, I show what's been produced in the detector, and then based off of our efficiency, I can show what's actually been detected. And so we see about 0.02 dineutron events per day within our detector. And then to understand the mutagenic response, and so this is really important to understand our dead time, as well as to understand the production of lithium-9, helium-8, and other radionuclides. We use an approximation from the Mannheim distribution, and so this is well detailed in PhysRub-D that I show right here. And so this describes our muon energy as well as the angular correlation of where the muons are coming from. And so you can see that most of them are downward facing muons. However, we do have some contributions from muons that are coming from the side. And so I plug this into our simulation framework to understand what light we're expected to see and the dead time that we're expected to see within our detector. And so we see about 1/10 of a hertz of muons within this detector. However, when we actually look at the veto response, I show in blue the background rate in hertz, and then in green is the muon hit rate, and then in black is our dead time. And so what we do is we look at how many times we see the muon hit rates relative to the background hit rate. And so in the background hit rate, again, similar to like our problems with our backgrounds, we have radioisotopes that are also going to trigger our veto PMTs. And so we want to have a veto limit that is ideal so that you can actually reduce the amount of muons that go through your detector, how many muons you see in your detector, but at the same time isn't triggering on noise. And so previous experiments use 4, a muon hit rate of about, or a veto PMT hit rate of about 4 PMTs as their trigger. We can actually go as far as using 8. Regardless, this gives us still like about 100% muon detection efficiency. And then we also use some information that was gained from using the WatchBoy result. And so they were able to show in this plot right here that if you just veto for about 30 microseconds, that should be significant for 1 microsecond, that should be significant to reduce the contributions from muon events. And so that's what we do in our detector. And then second to lastly, the mutagenic responses from the radionuclides. So again, I mentioned that you have these radionuclides that decay through beta and emission. And so these have a specific decay time based off of their half-lives. And so the problem with these radionuclides is that they live so long that you can't have a reasonable decay, you can't have a reasonable veto time to get rid of them. You actually have to accept them as backgrounds. And so what I've done is I've taken the production rate as determined through a Fluke simulation from Lee and Beacom analysis to determine what the radionuclides that would be produced in our detector are. So that's lithium-9, nitrogen-17, helium-8, and lithium-11. And if we look at the 1 microsecond veto time, these are events that we would be able to remove within 100% efficiency. And then we make an assumption about having a 90% tagging efficiency, similar to what SuperK is able to do with their radionuclides. And so these are events that we would actually be able to reduce by 90%. However, when we go further off into time, so greater than a second, these are events that we are just going to have to accept as background. And so that's mostly contributions from nitrogen-17 because it lives so long. However, if we look at the kinetic energy of these beta particles, specifically the prompt beta particle, not the neutron, we see that even though nitrogen-17 has such a long lifetime, its kinetic energy tends to have an endpoint close to about 3 MeV. So just by having a high, or not a high energy, by having a low energy threshold, you're going to remove a lot of the contributions from nitrogen-17. So it's actually not that strong of a contributor. However, you still see events from lithium-9 and then helium-8. And I mean, lithium-11, although it has a higher energy endpoint, it just produced a lot lower. And then also the timeline for the production is suitable. Okay, and then the last thing, the last background that we look into is spontaneous fissions from uranium-238 and thorium-232. And so we know that we have trace contributions of these isotopes within our water. And so you could imagine that if you had a fission event or spontaneous fission event from one of these two isotopes, if you saw a prompt gamma ray, and then a delayed neutron, that might look like a signal. Or if you were to see 2 neutrons in close time and space coincidence, that might also look like a signal. So we use the Freya fission model to correlate the gamma ray emissions as well as the neutron multiplicity distributions to understand what might still look like an inverse beta decay signal. And so for uranium-232 and for uranium-238 and thorium-232, we see this 2 multiplicity event, and that's how we actually determine our spontaneous fission background. And so if we actually look at the energy distribution or the PMT hit distribution for all of our signal and backgrounds, you can see our signal in blue for the prompt events, and then also again in blue for the delayed events, as well as the contributions from the world antineutrino backgrounds, the accidentals, the spontaneous fission, radionuclides, and then the fast neutrons for both our prompt and delayed events. And then if we actually look at our event summary, we would expect to see about 354 events for our signal, about 50 events for our world antineutrino background, which is again is our first single largest background in this detector, followed by our accidentals, which are about 30 events per year. Radionuclides and dineutrons are roughly 13 or 14 events per year. And then the spontaneous fission contributions is actually particularly small. So in total, we expect to see roughly 500 events within a year. So what we do to actually understand our sensitivity to different reactors is we develop these 2D distributions and use a Feldman-Cousins space confidence interval approach to actually understand what is not going to look like our background or what's not going to look like the signal that we were expected to see. And so based off of the prompt and delayed events, we look at the PMT hit time as well as the location within our detector wall that we plan on seeing. So we do this for both our random and coincident backgrounds. And then based off of these templates that we generate, we make likelihood fits to different reactor dwell times, different detector standoffs, and different thermal powers of nuclear facilities. And so when we do this and we understand our sensitivity, for a 90% confidence limit, we show to what extent we can reject different detector standoffs and different detector reactor powers. So in dark blue, this is everything that we can reject to greater than 3 sigma. So, and then in this lighter blue is what we can reject to greater than 2 sigma, and in this light blue color is what we can reject to greater than 1 sigma. And so where that becomes interesting is if we look at something like, again, a rock reactor or research reactor, that tends to be on the order of tens of gigawatts, again, tens of megawatts. And so what we see is that we can reject these to greater than 2 sigma on the order of like 5 kilometers away, right? So we couldn't really do like cross-country monitoring or verification of nuclear reactors. However, we could do a small region where we can exclude about a 5 to 10 kilometer radius for a small nuclear reactor. And again, if we were monitoring something like a large plutonium production facility, similar to what they had in Russia, you could imagine that you can actually reject those up to about like 50 kilometers if you're looking on the order of gigawatt scale nuclear reactors. And then when we look to see, well, can we actually confirm the nuclear reactor power or the standoff distance? What we've learned is that just due to our energy resolution, as well as our poor statistics, we can't actually determine whether or not there's a nuclear reactor extremely far away with a really high reactor power, or if there's a nuclear reactor that's really close by with a small reactor power. So we can't actually use our detector as it is right now to actually pinpoint the reactor power or the standoff distance. And if we revisit this antineutrino oscillations again, part of the problem is that a lot of these fast oscillations are going to be completely smeared out by a water detector because our resolution is about 30%, as well as the fact that if we, the reactors that we're looking at are 26 kilometers away, and so they're not so far away that this really slow oscillation component has kicked in, which is why we can't actually decipher the location. So it's possible that if we were looking at a nuclear reactor that might be further away with like infinite dwell time and infinite statistics, that we might be able to resolve like the slower oscillation feature. But right now, because we're at 26 kilometers, they all are going to look the same unless we have a higher energy resolution or even a lower threshold and/or a farther detector. Okay, so in summary, antineutrino monitoring has a capability to address many nuclear reactor safeguards programs and problems. So case studies and measurements have demonstrated the capabilities of antineutrino detectors to determine the power of reactors and determine the fissile inventory of multiple reactor designs. And the Advanced Instrumentation Testbed with gadolinium-doped water fill has the capability to monitor antineutrinos from nuclear reactors in the far field, expanding on the non-proliferation reach of antineutrino monitoring technology. And then also, if there's any students in the audience, there's a lot of postdoc positions that are open for both nuclear and particle physics and engineering. So feel free to check out any of these websites if you're interested in coming to Livermore. And thank you for your attention. And I guess I could ask if there's any questions.
Yes, well, thank you very much. Let's open it up for questions. We have some hands raised. How about Robbie? Robbie, you want to go first? Let's see, do I have to?
Yeah, so question is, how many like counts per minute or what count rate do you need to determine the fissile inventory of a reactor and to identify, whether or not it's being used for civilian nuclear power purposes or for malicious purposes? And what's the maximum distance that you can place your detector and get that information, get that count rate that you need?
Yeah, so the maximum count rate that you would probably need is something on the order of, to understand information about the fissile inventory, you would need something on the order of about hundreds of counts per day. And so that's unlikely to be done in the far field. And so that's usually why these near field detectors are more suitable. In the far field, really the most that we can do is determine whether or not a nuclear reactor is there, and then possibly where it may be. And when we talk about how far away we can actually be, it really determines it's really determined by your deployment site, as well as like how far down your detector actually is. So for instance, if we were to redo this entire analysis on the east coast of China, it would be very difficult for us to see anything because they have such large installed nuclear power there that you would just be overwhelmed by the backgrounds. However, if you were to do this in South America or even some places in Africa, you could actually see nuclear reactors at a lot larger standoff distance. And so you're no longer limited by the world reactor background. And then another issue then becomes, well, how far deep do you actually want to build your detector? And so one of the largest costs associated with building one of these detectors is excavating a cavern for it. And so based off of how shallow you make your detector, as well as, or how deep you make your detector, that also affects how well you can actually see a nuclear reactor. And so I guess there's not really like a ballpoint answer of like how far away you can go, but I guess we would assume probably on the orders of tens of kilometers, and at most maybe like 100 kilometers, as demonstrated by the Camland experiment.
Cool, thank you.
Let me ask you, there's a question here that was put on chat that I think is interesting, because I kind of thought the same thing. It says, the HM reactor is 6 times further than a Hartlepool reactor, but the flux contribution is about 1/8. Is there some reason why we don't have this 1/r² scaling that we would expect?
Yes. So the Haitian reactors have 4 nuclear reactors there, so they are a lot larger in flux, and so that's why they just have 4 reactors. Yeah.
Great, Devin. I saw you had your hand up. You want to go next?
Hi. Thank you for your presentation. I just wanted to make sure I was understanding something right. Could you go back to slide 11? So when you were talking about the antineutrino oscillations, especially that graph in the middle there about survival probability, could you explain again what you mean by survival probability? Because in my mind, I guess I'm trying to think of like Bragg peaks when you have protons coming through and they deposit all their energy at a certain distance based on the stopping power. But this isn't quite like that, right?
Right. So when I say survival probability, what I'm saying is that if I had a beam of antineutrinos and I went, let's say, 50 kilometers away, I would see, which is close to this dip right here, I would see about 3/10 of the beam of antineutrinos if I had an electron type antineutrino detector, because those antineutrinos, they wouldn't have disappeared, but they would have turned into a different flavor of an antineutrino. So in most of the cases, if you're detecting antineutrinos using inverse beta decay, you can only see electron type antineutrinos. However, along their trajectory to your detector, they will have oscillated to a different flavor. And so it's kind of awkward because there's not really any other analogy for it when you look at gamma rays or electrons, because they have just changed flavor eigenstates to being a whole different type of antineutrino that you can't actually see anymore through inverse beta decay, if that makes sense.
Yeah, that helps. Thank you very much.
I'm going to go back and forth to chat. So here's a chat question from Dr. Hayward. It says, you mentioned Super K neutrino observatory, which I think has been used to make certain observations of gigawatt thermal reactors as well. What do you expect to be understood with this purpose-built system, reactors at tens of kilometers standoff, that Super K cannot be used to understand? So I guess, what do you think this new detector is going to tell us that Super K wasn't able to tell us?
Right. So So I guess when we talk about these large antineutrino detectors, so Super K, I believe that was a detector that was alongside with SNO that was used that eventually got the Nobel Prize in 2015. And both of those detectors were made with water, right? So they just looked at electron scattering events. However, one criticism of this experiment that a lot of people have had is that Super Tomi Akindele is going to add gadolinium. Actually, they've already added gadolinium to their detector. So they're going to be gadolinium-doped water detector now. So that makes them more sensitive to antineutrinos. However, the closest nuclear reactor that they have to Super Tomi Akindele is on the order of like 200 kilometers away. And so they're unlikely to see a large contributions from their detector. Another thing that's also been mentioned is Super Tomi Akindele is a lot less clean than our detector would be. And when I say clean, I just mean that we're in a polyhalite mine, which is a salt mine. So we don't have, so even if we were like bring in trace amounts of like salt within our detector, we wouldn't see as much radiation increase in our detector as they would see. And so we're in a way better situated to actually measure the emission from a nuclear reactor than they are, based off of the fact that we're closer to a nuclear reactor. We have a cleaner detector. And then also we're going to see a lot less muon-induced backgrounds, just due to the fact that they're under a large, they're under a mountain, whereas we have a flat overburden, so we don't see as a larger contribution from a lot of the backgrounds that they would see. But yeah, that's a very fair criticism of like this project that we have to be mindful of.
Okay, we're going to limit to 2 more questions. Jalbin, are you there? I see you have a hand up.
Hello. Hello, Tommy. Thanks for the talk. So your detector is Cherenkov light based. But I don't recall that you mentioned the directionality of the neutrinos. So is that possible? You can detect where the neutrino is coming from, and also maybe after some data taking time, some accumulation of data, you could maybe use the directions to use as a cut to reduce the background, because mostly like the neutrinos will be coming from only 2 reactors in a specific angle relative to the detector. Thanks.
Yeah, that's a really great question. And so when we talk about directionality with antineutrino detectors, you can really determine directionality in one of 2 ways. So you could either do it through neutrino electron scattering. And so that's what Snow and Supercomio Conde did. But what's important to note about their detectors is when you do electron elastic scattering, you're now completely blind to the flavor of the antineutrino. So you would affect it, or whether you're completely blind to whether it's an antineutrino or a neutrino, as well as like the flavor, so electron, muon, tau, etc. However, when you're looking at neutrinos from the sun, they are significantly higher in energy than when you're looking at an antineutrino from a nuclear reactor. And so they're able to do it through scattering, they're able to do directionality from scattering because they have significantly more energy. So you can actually see that recoiled electron or that scattered electron a lot better than you could if you were using antineutrinos that scattered on electrons. Another way that you can do directionality using inverse beta decay, and that was another thing, is that process doesn't use inverse beta decay, so we would be more sensitive to our singles backgrounds instead of requiring a coincidence, right? Using a prompt and delayed event makes it a lot easier to actually see your signal. But another way that you could use it with inverse beta decay is that I mentioned before that the antineutrino, when you have inverse beta decay, that the positron is going to carry most of the kinetic energy of that particle, whereas the neutron is actually going to carry a lot of the momentum. But the problem with the neutron carrying momentum is that then the neutron scatters around a million different times before getting captured. And because the neutron scattering on proton is going to be like a 1-to-1 collision, it's likely that you're going to lose a lot of directional information. But on average, that neutron should travel further ahead than the actual positron. And so you could do some sort of, if you had better reconstruction than we do, you could on average look at where that positron versus that neutron is reconstructing in location and determine where that nuclear reactor could be. However, that usually requires a scintillator detector, because in that case you would have better positional sensitivity than we do. And since we can't really see anything other than 2 meters apart, we wouldn't be able to do that with our detector. We are, however, looking at neutrino electron scattering, but right now it looks like the #1 contribution that's going to make that difficult for us is going to be the radon that could be emanated from our PMTs. So that is something that's being looked at, but it's not something that we, it's more of like a stretch goal than something that we could actually do in the near term.
Great. I'm going to let Dr. Halbron ask the last question. I saw he had his hand up early and then he threw one up into chat. And I'd like to thank you, Dr. Akindele. I have to run, but Dr. Hayward's going to close out for me. So Lawrence, it's on you.
Great, thanks Wes. Thanks for the talk, Tomi, it was very nice. The big had, actually you may not be able to answer because you mentioned that you compared your experimental results to J-ONT4 and Fluka calculations. And I was just surprised to see that the J-ONT4 calculations were so far off. And I understand another student did the simulations, but do you happen to know the physics models that were used both in J-ONT4 and the Fluka simulations by any chance?
So I'm not sure what model she used in Fluka, but there is a paper on this, and I should have actually cited this in this talk. But I do know that the models, it was like the shielding physics list was what was used in J-ONT4.
Okay.
That didn't agree.
Interesting. Okay. Yeah. Thank you. Again, very nice talk. Thank you, Tomi.
Yeah.
Okay, and with that, I think we're over on time. So I just want to thank you again. Appreciate your time, Dr. Akindele, for joining us. It was a really interesting talk, and that's all for today. Thanks, everybody.